And this is where we're going to start talking about kinetic diagrams, and we're going to start talking about what you need to solve the equations of rotational motion. So far we had figured out the equations of motion, but the equations of motion just had linear acceleration involved, just an A. And now we need to bring in alpha. And so how we're going to do that is we have to look at this equation, the sum of the moments equal I, G, alpha. And what that's saying is the sum of the moments about a point. In this case, it's the center of mass, but it doesn't have to be. The sum of the moments about a point are going to be equal to the moment of inertia about that same point times alpha. Remember, each rigid body has a single alpha. The rigid body can't have multiple alphas, so the alpha is not about a certain point. Only the moment of inertia and the moments are about a certain point. The alpha is the same for the entire rigid body. So if we were to go to a different point, let's say we moved from G to P. We are now at P. We could write a very similar equation. We could say sum of the moments about point P is equal to the moment of inertia about point B times alpha. We also know something about how to relate the moment of inertia of P and the moment of inertia of G. How can I relate those two? Parallel axis theorem. Very good. So parallel axis theorem, we have IP is equal to IG plus MD squared. What we're going to do is we're going to plug that in. We're going to go ahead and plug that into this equation here. And we'll say sum of the moments about P is equal to IG plus MD squared times alpha. And then we can say, well, the sum of the moments about point P is equal to, I'm going to bring alpha in and distribute it through that equation. IG times alpha plus md squared times alpha. We can also say that d, the distance from here to here, that's my d. That's that perpendicular distance from G to P. I can break that up into two components. I could break that up and I could say, well, there's going to be an x component and a y component. That x component I'm going to call x bar, and that y component I'm going to call y bar. Why x bar and y bar? Because that's the location to our center of mass. When we learned center of mass and centroid in statics, we always use that same notation. X bar and y bar was the location of the center of mass, and G is our center of gravity, which is the same thing as the center of mass if we have a uniform gravitational field, which we do on Earth. If I have this triangle, I've got my d squared, I've got my x squared, and I've got my y squared. And I can say that x squared plus y squared equals d squared. And I can plug that in. So I say sum of the moments about P are going to be equal to I, G, alpha, plus m times x squared plus y squared alpha. I now have IG alpha plus m x alpha times x plus m y alpha times y. So kind of weird, but mathematically correct, right? Okay, I want to show you why I did that. What is x alpha? X alpha is going to change into AGY times x bar. And y alpha is going to change into AGX times y bar. Okay? This equation I'm just going to reorder to make it look like what it shows in the textbook, and then I'm going to try to explain again in a little more detail why it's important. That the sum of the moments about P can either be calculated by finding the moment of inertia about P and multiplying it by alpha, or by taking the kinetic moments. What the kinetic moments are is us saying for a second, we know F equals ma. We normally look at the left-hand side of that equation. We know that anything on two sides of an equal sign, both sides are equal. And we can look on the right-hand side and we can say, well, what if we ignore the forces for now, and we just said this acceleration is a vector, and it has multiple components. this relates directly back to statics. When we did, at the very end of statics, I believe, we started doing equivalent systems. So what we're saying is that there are some forces acting on this, and that's going to cause some sort of acceleration. We could make an equivalent system that just has two forces acting at the center of mass. Those two forces are going to be equivalent to m times our two components of acceleration. Once we know where it moves, we can make an equivalent system and call those pseudo forces. So what we're going to do is we're going to come up with a very easy way to draw two diagrams that we know are equivalent to each other. On the left-hand side, we have our free body diagram. I'm changing nothing about your free body diagram except for saying draw your full body. So for everything on the left-hand side of the equal sign, I'm looking at my free body diagram. Everything on the right-hand side of the equal sign, all of this, I'm going to draw a kinetic diagram. A kinetic diagram is very, very simple to draw. Way simpler than a free body diagram. Why? Because we're going to have the same components every single time. We're going to draw an object. We're going to draw its center of mass. And we're going to draw components of acceleration. M, A, G, X, M, A, G, Y. Notice that that's mass times acceleration, which we know is equivalent to a force. So these are pseudo forces. It's almost as if we're drawing a free body diagram. MAGX, MAGY. Now those could be NT, those could be R theta Z. It doesn't matter which coordinate system you choose. Yeah, they come from us realizing that F equals MA. And if F equals MA, on the left-hand side, all of the forces have to add up. On the right-hand side, all the accelerations have to add up. So we're drawing an equivalent system where we're saying, up here, this is what's actually happening. We can imagine it as if all of the forces were acting at the center of mass. And then there's rotation. We're doing the exact same thing we did in relative motion. We're saying, let's take that rotation and the translation and separate it up. So for each and every body, we can draw a diagram where we have the sum of all of the forces acting on the center of mass, and we'll just call that MAGY and MAGX. And we have the rotation about that center of mass, which we call IG alpha. Now we can do the sum of the moments, and these are called kinetic moments. They use kind of a funny summation sign, or they use a funny M. They use the sum of the funny M, subscript K, and you'll see it in the textbook, is going to be equal to, now we just look at the right-hand side and treat it like a free body diagram. Pretend for a second that these are forces, and pretend that that's a couple moment. Okay? We have point P over here, and we're going to say, okay, if I find all of the moments, kinetic moments about point P, well, that's as easy as saying, what's this distance? That distance is x bar. And if I put my thumb on P and I point my fingers towards this force, it would tend to curl my fingers. So it would be MAGY times x bar is one moment about P. X bar MAGY. And then we're going to look at this distance, which is the distance to the line of action. We'll call that y bar. And this is what Raymond was saying earlier. I just didn't want to jump there. If we go to P, we put our thumb on P, we point our fingers up. Notice my fingers are bent back with this arrow. And so there's a negative sign. It would be a negative moment of MAGX times y bar. Once you choose your coordinate system, what you're saying is, I'm choosing an equivalent system where we have pseudo forces acting in the directions I chose. And I know that this has to be equivalent to that because I know in general planar motion I have linear acceleration as well as rotation, angular. And then we say, okay, well, the couple moment, we got to add that on, so we're going to be plus IG times alpha. Basically, the only thing a kinetic diagram gives us is the ability to quickly come up with this equation and relate it to the summation of all the forces on the other side, giving us an equation that allows us to solve the problems by using IGs, the acceleration of that center of mass, and the moment of inertia about that center of mass. Why is that helpful? Well, most of the time when we're looking at an object that we recognize, we can look up the center of mass in the back of the book. Whereas we can't do that if we're using another point somewhere. So this free body diagram, called a kinetic diagram, is a shortcut to get your equation.